I had a funny experience one time. I was attending a large irrigation conference in Phoenix, and we were taking a survey of the landscape irrigation professionals as part of our landscape irrigation evaluation project. And so I asked one of the leading contractors how he determined the length of time to leave the controller on and the amount of water each plant needed and how he adjusted the number of emitters per plant. And he said, that's your job. And I was just completely taken aback by that. It was like, that's my job, but you put the systems in. I mean, I didn't say this. You put the systems in and you don't even know how to adjust the number of emitters per plant or the controller. And actually, yes, the contractors don't know how to adjust the number of emitters per plant or the controller. And when he said that's my job, I mean, how am I going to go out and adjust all these emitters? But now with online irrigation controllers, they can from the office or the program adjust the length of time the controller's on. And well, I made a spreadsheet to adjust the number of emitters per plant, which I'll share with you. But I think now we are at the point where we can adjust the controllers and the number of emitters for people through the online irrigation controllers. And I included several videos in the irrigation systems design playlist that go through some of those controllers. It's very interesting. Okay, this is the outline. I'm just going to go through some of the steps in designing a landscape irrigation system. So the first step is to make a drawing of the property. And then the next step is to determine the flow rate for the system, which is generally based on the size of the flow meter that the city has installed for the home. And then we'll calculate the plant water requirements. And I won't go into actually designing the pipe system, but basically you just need to make a big enough trench to hold all your pipes wherever they're going. And you can pretty much use all 1-inch pipe in a small or semi-small yard because the city flow rate is generally less than 10 gallons per minute or in that range, and 1-inch pipe will carry that flow rate. So rather than having a bunch of different 3/4 and 1-inch pipe fittings, you can just get one size of pipe. It saves on trips to Home Depot. So the first step is a site visit or an owner interview. And what we used to do is, you can see this graph paper here with lines. We used to have to either ourselves or the homeowner give them a graph paper and have them draw out the entire property. But now you can pretty much just use Google Maps and they'll get close enough to the property to be able to see the individual plants or the individual zones. The next step is to note the location of obstructions. For example, you wouldn't want a sprinkler right next to a tree because it wouldn't spray on the other side of the tree. And then you need to know the location of the water source. And so that would either be at the location of the water meter or at the location where the service line runs into the house. You generally want to tap into the pipeline before it goes through the house because you have better pressure. Then you need to know where any walls are because you wouldn't want to spray sprinkler water on walls and discolor them or otherwise degrade them. You need to know where the concrete or asphalt is because you'll either have to go around or under it. Of course, you'll need to know where the turf areas are. And one thing about landscape architects is they do not design their landscapes based on the irrigation designer's needs. So then it might be quite challenging to place, as I showed in the previous video, to place the sprinklers so that you have an efficient and uniform application. Then, of course, you would draw in the tree and shrub areas. And one thing you should note is the wind speed and direction. Okay, so I never drank coffee prior to becoming an irrigation engineer. But what I learned is that you need to sit down with a customer and discuss their system and personal requirements with them. And this generally happened over a cup of coffee. So I would drive out to the farm in my S10 Chevy pickup and do a site visit and owner interview. And then I would go back to the office and design the system. But whether a farm or an urban irrigation system, you want to find out the following from the owner or from local codes. How long do they expect the system to last? What are the local backflow prevention requirements? So the owner probably will not know this, but you can discuss the pros and cons of different backflow prevention technologies within the constraints of the local building codes. You should also discuss whether they would like an extra solenoid master valve. So every once in a while, a solenoid valve leaks or fails to close. And if you have an upstream master valve, then the system does not continue running if it's supposed to be off. You can also get flow meter alarms that detect if there's a leak. There's many controller options that you can discuss with the owner, ranging from manually turning on a valve, a timer on a hose, an automatic controller with soil moisture sensors in the ground, or Wi-Fi systems, as I just discussed before, that are controlled based on the weather. You should find out from the owner their level of concern about irrigation efficiency, saving water and water cost, and find out the price of the water if you do not know. So it might be very important to have a water conserving system, or it might not be so important. Let's say they have their own well and it doesn't cost them hardly anything to pump the water. The primary concern of most buyers is the price of the system. That's how the decision is made to either purchase or not purchase a system, or to purchase from your irrigation company or a different irrigation company. The source of water and expected components will lead to a filter choice. So in general, a simple inline screen filter is sufficient for urban potable water systems, even for drip irrigation. And then you need to find out the operating pressure. So you can call the city about the pressure, but you can also bring out a gauge and a bucket to measure the flow rate and pressure if necessary. Pressure regulation should be mentioned, discussing the benefits of lowering the pressure. There's some cases where the urban water pressure is low, where you wouldn't want to further decrease it by adding a pressure regulator. But in general, you want a pressure regulator because the city water pressure varies. Okay, so like I said, we used to have to go out and draw maps, but now it looks like you can just start with, this is Google Maps, and make a digital image. And I actually, when I started this lecture, I looked for drone and satellite mapping systems, but it looks like Google Maps is probably what everybody uses. Actually, I can zero in here and I can even see individual plants. So I guess Google Maps is the de facto source of drawing information. And then I also noticed this product that can work with Google Maps to lay out the plants in the yard. And they also, if you look here, they have an irrigation design tool within the software. I don't know what that does, but you can get I'm not selling this because I don't even know them, but just for reference, you can get a personal version for $150 or a professional version for $500. If the site was designed by a landscape architect, then you can start with their PDF drawing of the property. And this was an irrigation design that I worked on for a park in Aqaba, Jordan. I just overlaid the irrigation system over the landscape architect's system. And you can see I used my coiled inline drip around the trees. And I tried to use the inline tubing in the gardens. I think this was before the small inline tubing. So I was trying to snake it through. But anyway, you can draw your pipe network and your solenoid valves at the beginning of each zone. Notice I've separated different kinds of plants into different pipe solenoid valves. And so that's a nice start, just to start with the landscape architect's design. Unfortunately, this garden was never constructed. Okay, and here's a picture of a landscape professional um, with his watch and timing the rate that the water fills up the bucket. So that could give you an idea of the flow rate. And also you could bring a hose, a pressure gauge to the property, a hose mounted pressure gauge. So you could just screw it onto the hose bit and find out what the pressure is at the property. Okay, these are just some rules of thumb from Rainbird. So the pressure loss through the water meter should not exceed 10% of the minimum static water pressure available in the city main. So when you decide your flow rate, that's going to result in a certain water pressure loss in the water meter. And so your flow rate should not, your water loss, your pressure loss in the water meter should not exceed 10% of the static water pressure in the city main. The second rule of thumb is that the maximum flow through the meter for irrigation should not exceed 75% of the maximum safe flow of the meter. And I'll show you how that works. And then the velocity of flow in the service line, so that's the line going from the city to the house, should not exceed 5 or 7.5 feet per second for PVC or copper pipe respectively. So higher velocity is allowed in copper because it's rated at 400 PSI versus about 100 PSI for PVC pipe. So this picture is based on a Rainbird example of a typical urban service line. So this is, we're looking down the street here. So this is the city water main going down the street. So it's at 111 PSI, which is 78 meters pressure. And then we have 1.5 inch pipe, and we have a couple 1.5 inch 90s. And then we have a manual shutoff valve. So this would be the shutoff valve for the property. And these are 3/4 inch, this manual shutoff valve and the water meter. So this is a 3/4 inch water meter. It sounds kind of small, but actually that's bigger than some. Many properties have a 5/8 inch water meter. And then it goes through 35 feet of 3/4 inch copper pipe. Now you can just use PVC pipe up to the house. And then you would cut into the pipeline and take your irrigation system off before it goes into the house. So here's just an example calculation for the maximum flow rate to the zone. And we're going to do it for the 3/4 inch pipe. So the goal is, this says 2/3 meters per second, but we don't want more than 2.3 meters per second. So what flow can we handle through the 3/4 inch pipe, the 18.9 millimeter? Well, the flow is the velocity times the area. We can't have more than 2.3 meters per second. So we multiply that times the cross-sectional area, and we can have 0.645 liters per second, or 38.7 liters per minute, or 10 gallons per minute, which is the maximum flow rate that you generally use in a home. Okay, and here's some sample calculations for the pressure loss. And so this is the 1.5 inch copper. We had 7 meters of, 1.5 inch, 1.5 inch copper. We had 7 meters of that. And this is the Darcy-Weisbach equation. And this is the diameter of the 1.5 inch pipe. And this is the flow rate, 0.645 liters per second, or 10 gallons per minute. So we have almost no pressure loss in the 1.5 inch copper pipe. But in the 3/4 inch copper pipe, we have 3.9 meters pressure loss. But even then, the city water pressure is 111 PSI or 78 meters. So 3.9 meters pressure loss is not bad. And then we can check the pressure loss in the flow meter against the city water pressure. And so if we have 37.85 liters per minute, that if we look at this table in the catalog worksheet in your spreadsheet, your pipe design spreadsheet, it shows that the pressure loss is 11 kPascals, which is the same as 0.11 bar or 1.2 meters. And because the city water pressure is 78 meters and we're only losing 1.2 meters in the flow meter, that's acceptable according to that 10% rule of thumb. And then you can check to see that the flow is not greater than the 75% of the maximum flow. And so this is just a table of flow rates for this 3/4 inch flow meter. And if they have a number, that means that's a safe flow. And so the maximum safe flow is 94 liters per minute in the 3/4 inch flow meter. And we only have 37.85, which is less than half. So yes, we do meet the rule of thumb criteria for the flow of 37.85 liters per minute. So then we can calculate the total friction loss in the service line. And so we add the 3.9 meters friction loss in the 3/4 inch pipe section. We have a 1.2 meters pressure loss in the water meter. We have 1.5 meters elevation gain, and we have 0.09 meters pressure loss in the 1.5 inch copper pipe. And so then we have 71 meters pressure after subtracting all those from 78. So that's well within the range we need for, actually, we need a pressure regulator so we don't blow the system apart. Very high pressure. Okay, and I'm going to show you a spreadsheet where I'm going to calculate the friction loss in the different components of the service line, like the 90s and so on. And one way that you can calculate the friction loss in a 90 is put in the minor loss coefficient and multiply by V squared over 2G. Another way to do it, and that's the way I've done it in this example, is to use an equivalent length of the fitting. And so, for example, if L over D is 20 and the diameter is 10 centimeters, then the equivalent length of pipe for the fitting is 2 meters. And so you just substitute the 2 in here with the diameter of the fitting at the given flow rate, and then you can calculate the head loss in the fitting. So here is the spreadsheet that you can use to calculate the pressure loss in the different parts of the service line network. And then, of course, you could do the same thing with the pipes going out to the irrigation zones. So here we have a sudden contraction, and instead of a minor loss coefficient, we have an equivalent length of pipe. So the equivalent length of pipe is 28 times the diameter. So 28 times 37.9 millimeters. I think that's the diameter of 1.5 inch pipe. Then we have an inside diameter for the copper pipe. We have a 90-degree elbow. The L over D is 25. And if you look in the catalog spreadsheet, you'll see that opposite these fittings, which you access here in the drop-down menu, but they refer to the table in the catalog spreadsheet. You'll see that the pipe, the L over D is 25 for this fitting. Then we have more copper pipe. Then we have another fitting. Then we have more copper pipe, another fitting where we're contracting down to 3/4 inch. We have a gate valve at 3/4 inch. Then we have the water meter. And if you remember, the water meter uses these tables. And I have some codes to determine which column I'm in and so on. So it'll find the pressure loss in the water meter. And then here's the last 3/4 inch copper pipe. And um, I think that was 11 meters long. So you can add up all the friction losses and come up with the 71 meters pressure at the end of the pipeline. So I don't think I'll go through this spreadsheet by activating the Excel spreadsheet because I think I just explained it. But one thing it also has is these rules of thumb. It determines whether the rules of thumb are okay. And then you list the number of components here, 10. So we had 10 components here. Here's the inlet elevation, the pressure at the city main. And then we have the discharge elevation. So that's where that 1.5 meter increase in elevation was. So anyway, it comes up with the 71 meters hit. Okay, let's move on to plant water requirements. So as you can imagine, with 3,000 different types of landscape plants, potential types, it's rather difficult to obtain a crop coefficient for each. But Costello and Jones in 2014 in California, they organized some committees of landscape architects and they assigned crop coefficients, or what's called landscape coefficients, to all the types of plants that were used in California. Now, as you can imagine, these aren't accurate or scientifically verified, but they're not too bad. For example, we're going to use an orange tree crop coefficient of 1.0. Maybe a mesquite tree might have a crop coefficient of 0.25. So you can get some general ideas, and then people have done research on the topic also. But that's a limited number of plants, but there has been some research that you can find in the literature. One of the problems with these landscape coefficients in the desert is that desert plants will take as much water as you give them, and many can survive with no water, for an entire summer, for example, with no rain or irrigation. So I guess we should take this crop coefficient information with a grain of salt. In general, desert plants, if you water them too much, they'll just grow more, and then the people have to do more pruning. So obviously, you'd want to consult with the owner about how much he wants to water, particularly his desert plants, his or her desert plants. Okay, this is the landscape coefficient method developed by Costello and Jones. It's quite good. I really like it. So instead of just a crop coefficient like we have in agriculture, we have a species coefficient representing the plant. We have a microclimate coefficient representing the location in the landscape. For example, if a plant is right by a street, it might be hotter. If it's in the shade of a building, it might not be as hot, and so it wouldn't have as much evaporation. And then a density factor. For example, if you had trees over grass, then the landscape as a whole might even have more evaporation than just the trees themselves, of course. So anyway, you multiply these three coefficients together and you come up with the landscape coefficient. Okay, so this is Costello and Jones' guide online called WUCalls. You can just type WUCalls. Obviously, there's not a lot of WUCalls on the internet, but the document is available as a PDF or as an Excel spreadsheet, and they just list for every type of plant, both the common name and the scientific name. And for every zone in California, they list the species coefficient. So in general, they say a high species coefficient is 70 to 90% of reference ET, moderate is 40 to 60% of reference ET, low is 10 to 30% of reference ET, and very low is 10%. And like I said, it's based on opinions of landscape architects. Okay, so what they do is they have divided California into these zones. And so in Tucson or Maricopa or Phoenix, we would be in the low desert zone. So we're in region 6, but because the spreadsheet's so long, I couldn't show region 6. But anyway, they list the type of plant, both the botanical name, the common name, and then they list the basically the crop coefficient. So this might be a species coefficient of 0.5, since they're listing 40 to 60% of reference ET. And then not applicable, I suppose that means they wouldn't grow um, Abelia, whatever, in region 1, that kind of thing. But you can download that spreadsheet. One of the interesting things was the turfgrass species factors. So our summer grasses, such as Bermuda grass, have a low crop coefficient, 0.6 in summer, and 0.4 if you want to deficit irrigate it. Like I walked by a school today with almost all brown grass, so that would be lower than 0.4. But our winter grass is ryegrass, which has a crop coefficient of 80%. But the thing about the crop coefficient of 80% is that the reference evapotranspiration is 1/4 of the summer. So really, they don't use that much water. And just in general, it's interesting to see that the grasses really, they don't have like a 1.0 crop coefficient. They're lower than 1.0. And so that's one reason grass isn't so bad to have in the desert. Although with no rain, of course, we wouldn't want to have any grass. Like this year, we have no rain. Okay. Um, let's look at the density factor. So that's based on tiers and density. The density factor is 1.0 if tree cover is greater than 70% or shrub cover is more than 90%. Landscapes planted in tiers have density factors between 1.1 and 1.3. And the density factor might be between 0.5 to 0.9 for low density. So they're looking at the landscape as a whole, not just one individual tree. And then the microclimate factor, plantings near roads or sunny sides of buildings or in wind can have a microclimate factor between 1.1 and 1.4. The microclimate factor is 1.0 for just an open area, or 0.5 to 0.9 for plants in shade or protected from wind. Okay, so for the irrigation schedule, there's 4 steps. First, we need to calculate the plant water use. Then we need to calculate the soil water storage under the plant. Then we need to calculate the days between irrigations, or the potential days between irrigations. We wouldn't necessarily go with the calculated value here, but that would be the storage over the liters per day requirement of the plant. And then you'd calculate the irrigation runtime. And actually, I don't think this is necessarily right. I think you should calculate your irrigation runtime as the liters per day required by the plant and the number of days that you decide on between irrigations, and then divide that by the emitter flow rate. Of course, if you did go with this number, just S over liters per day, like 4.5, then you would have an irrigation runtime that corresponds with S over Q. But as you'll see, we're not going to choose that number ever, because you need to have an integer number of days between irrigations. Okay, so the plant water use, the liters per day, you can do all this unit conversion, and then you come up with the liters per day is the evapotranspiration rate for the plant in millimeters per day, basically times the area of the plant. And then you can divide by the irrigation efficiency here, which I do sometimes, but in the spreadsheet, I don't divide by the irrigation efficiency initially. I put it at the end when I figure out my irrigation run time. And then your soil water storage for an individual emitter or bubbler, so it has a circular wetting pattern. It's the area times the depth of the root zone times the available water capacity, so the difference between fill capacity and permanent wilting point, times the MAD, management allowable depletion, and then times 1,000. And then that would give you the soil water storage in liters, 1,000 liters per meters cubed. So we're meters cubed over here, convert to liters here. So that's the equation. One thing to be concerned about is you might have a root zone depth, but it's possible the roots aren't very developed in the lower zone, so you wouldn't want to depend, lower part of the root zone, so you wouldn't want to depend on water in that part of the root zone. So you might multiply your root zone depth times 62% or 0.62 to get the actual effective root depth. So you might not be able to utilize the entire root depth, even though the plants might have a few roots down at the lower levels. Okay, so this is my irrigation design spreadsheet, or plant water use spreadsheet and irrigation scheduling spreadsheet. And so I had a more complex landscape irrigation spreadsheet or Excel program in the past, but it was difficult to learn from in these class exercises, and it was prone to failure. So I made this simple spreadsheet, which calculates the water requirements and schedule for the plants in a zone. And so the user needs to input the data in the white cells, and the spreadsheet calculates the water requirements and possible irrigation schedule in the yellow cells. Column M has the root zone depth. So actually, I'm just going to read this off. I'm not going to try to find them. That would be hopeless. Cell B4 has the fraction of the root zone utilized by the plant. So that's where you can see here it is 0.62. If you use that 40-30-20-10 rule. Cell B5 has the irrigation efficiency. And so this is, remember, that could be used here for the liters per day requirement, or it can be used over here to increase the irrigation runtime to account for the lack of efficiency. Cell B7 has the available water capacity, or the AWC. And cell B8 has the reference evapotranspiration rate. And cell B9 has the management allowable depletion. And after the spreadsheet calculates a possible irrigation schedule in number of days between irrigations here in column S, then the user puts in the actual. So maybe it would even calculate 3 or 4, but you decide, well, I want to irrigate every other day. So you just put a 2 here. Here it's calculated 1.03, so I put 1 day between irrigations. And then it calculates an irrigation runtime. And then you can select a different runtime if you want. And then it'll give you a different number of days between irrigations, possibly. So the important thing to remember is you put the information in the white cells, and it does all the calculations in the yellow cells. So this is our first example. And this is an acacia tree with a well around it. We have a bubbler, a 2-meter diameter, and 8 liters per minute flow rate. Also, we're going to look at whether if we irrigated it with 4 emitters. And so those would have a 0.6 meter diameter wetted area and 4 liters per hour per emitter. So this is liters per minute. This is liters per hour. The landscape coefficient for the acacia tree is 0.3. Reference ET is 12 millimeters per day. And I don't think I said it before, but you always design for the maximum reference ET in the middle of the summer. The assumption is the owner can irrigate less during the other parts of the year. And then for this orange tree, the MAD, or this acacia tree, the MAD is 0.8. The efficiency of the irrigation system is 80%. AWC is 0.08. So these are the example calculations. And the first step in the calculation of the plant water requirement is to find the evapotranspiration rate. So first, the landscape coefficient is the product of the species coefficient, microclimate coefficient, and density coefficient. And in this case, the tree is in a a hot location. The species coefficient here is 0.25. So the overall landscape coefficient is 0.3. And then if we multiply the landscape coefficient times the reference ET, then we have 3.6 millimeters per day. So that would be like the equivalent vertical transpiration of water of 3.6 millimeters depth per day. Then the liters per day is this plant evapotranspiration rate times the area of the plant. And here I divided by the efficiency, so 31.8 liters per day. But if I didn't divide by the efficiency, it would be 25 liters per day. And that's the number I'm going to use in the spreadsheet. Okay, and then we can calculate the soil water storage. So remember the AWC, difference between fill capacity and permanent wilting point, is 0.08. The MAD is 0.8 because it's a desert plant, so it can use almost all the water. So if we multiply all these numbers together, we get 200 liters of water storage. So the days between irrigation, at least the potential days, is 6 days. We need an integer number here. This actually isn't exactly 6. And then the minutes would be the storage over the liters per minute. And actually, it's not the storage, it's the, I think it's 192 liters per day over 8 liters per minute equals 24 minutes. And so in the spreadsheet, the days equals 200 over 25, not 32, or 8 days instead of 6 days. Remember, I have 32 here because I included the irrigation efficiency in that calculation. And then we can do the same calculation for the drippers. It looks like this came through a little blurry, but we have 4 drippers. And then we have the diameter squared and the 70, 80 number. And so that's 72 liters of storage. So for the drip emitters, the days between irrigations is 2, and the hours of watering for 2 days is 4 hours, or 32 times 2 is 2 days, over the 4 by 4 liters per hour, 4 hours. This is the spreadsheet. So like I said, I only calculated 25 liters per day without the efficiency number. And then you put in the plant diameter, the landscape crop coefficient, the number of emitters. And so for the drip, it's 4. For the bubbler, it's 1. Then here's the liters per minute per emitter. So this is the 4 liters per hour is 0.067 liters per minute. Here's the 8 liters per minute for the bubbler. And so this would be the flow per plant. So it's 4 times 0.67, and this one is just 8. And then we have the root depth, the wetted diameter, the emitter spacing. And the thing about the emitter spacing here is this has an if-then statement. And if it's a hedge, then you give this a length. But if it's just a plant, you let it be 0, and it'll calculate it as a plant or a cylindrical, circular geometry. So the wetted area is 1.13. The available water under that wetted area of the drip emitters is 72. For the bubblers, it's 201. So then you decide on an irrigation schedule. And in this case, we're just going to say we're going to irrigate the drip every 2 days, the bubblers every 6 days. And this is why you don't put bubblers and drippers or different types of irrigation application devices on the same zone. So you never want to mix drippers with like sprinklers or bubblers, because you're just going to way overwater the other system just to water enough with the drip. So anyway, here's the irrigation runtime for the drippers, 238 minutes, and for the bubblers, 23 minutes. And so then we're going to select a runtime of 240 and 24, which is not really much different than that. But anyway, that's your last selection. Okay, let's look at example 16.3, which is for an orange tree. And because of the high water use, we need many drippers in order to avoid having to leave the drip system on constantly. And the answer to that problem is a coil of inline drip tubing around the tree. Unfortunately, this is Midjourney bot AI, did not understand that I wanted a nice engineered coil rather than just a random hose on the ground. but I think AI did a pretty good job of making the relative sizes of the 8-meter canopy and the 4-meter diameter coil. So not complaining. I was pretty surprised that they were able to do this. But anyway, in this case, we have an 8-meter diameter orange tree. Reference ET is 12. The crop or species coefficient is 1. We have an individual tree, so density and microclimate factors are 1. It's a coil, and the coil has 4-meter diameter, total flow rate 180 liters per hour. So we can just treat it like an individual emitter with those flow and dimensions. The root zone is 2 meters, MAD is 0.5, efficiency is 0.8. In this case, we're not utilizing the entire root zone, so we're only using 62% because of the 40-30-20-10 rule. And then the AWC is 0.08. So the book actually has this number wrong. It should be 753 liters per day. So you can go through this if you want. This includes the irrigation efficiency. And then we can calculate the storage also based on the diameter of the coil, which is 4 meters. And so we have 619 liters of storage. And then the watering required per day would be 753 liters per day divided by 180 liters per hour, or 4.3 hours per day. Okay, and here's the example in the text. I don't know if this should be 16.2, but anyway, I think it might be 16.3. The plant diameter is 8. The landscape crop coefficient is 1. So here's our 600 liters per day water use without the efficiency in that calculation. Here's the liters per minute per emitter. So that was 180 liters per hour. So it's 3 liters per minute for the coil. So the wetted diameter is 4. So here's the wetted area, 12.6, and the available water is 623. So you can see that our water use, our requirement in liters per day is about equal to the applied water. And so we can have 1 day between irrigations. And then the irrigation runtime, we'd actually be putting on 753 liters here in 251 minutes. So, or 4 hours. So that's where that efficiency calculation comes in. It adds to the irrigation runtime. Okay, the next example is for a hedge or a landscaped area, an irrigation system needs to be designed not to water a single tree, but based on a square area. And in the case of the plant, the area is multiplied by ET to find the liters per day. So here's the area of the plant. I just showed here how the units all cancel out. And here's the landscape evapotranspiration rate. And I divided by the irrigation efficiency here, but again, I didn't do that in my spreadsheet. So in the case of a hedge with inline emitters, you can calculate the area for the evapotranspiration as the product of the distance between emitters and the wetted width W. So instead of just calculating a water use requirement for the whole hedge, what you can do is you can just divide it into the zone of each emitter. So that way you don't have to worry about the length of the entire hedge. You can just design your schedule based on the area watered by one emitter. And then the wetted area per emitter is just the length between emitters and the wetted width of each emitter. So that's how we're going to calculate that. So here's the equation. So we just have area. So that's the area of one emitter, basically, for the storage, the wetted area of one emitter. And then other terms are the same. So here's our example. We have an oleander hedge, and we have a 1.5 meter hedge with 4 liters per hour emitters that are 0.3 meters apart. The species coefficient for oleander, which is a relatively low water use plant, is 0.5. And the microclimate coefficient is 1.3 since it's on the south side of the building. The root zone depth is 2 meters. The MAD is 0.5. The irrigation efficiency is 80%. And the root extraction is not weighted, so the effective root depth is also 2. So in this case, the landscape coefficient is 0.65 because the microclimate was 1.3, the species is 0.5, and then the evapotranspiration rate is 0.65 times 8 millimeters per day. I forgot to mention that. That's the evapotranspiration rate for this oleander. And then so we have a landscape evapotranspiration rate of 5.2 millimeters per day. And then the liters per day for the area of one emitter is 2.9 liters per day. Without putting the efficiency down here, I think it's 2.3 liters per day. And then the soil water storage, again, we just use the distance between emitters and the wetted width of the emitter. So the storage is 14.4 liters. So then the days between irrigations is the storage over the liters per day, or 5 days. And then the runtime would be 14.4 liters over 4 liters per hour, or we could use the 2.9 times 5 over 4 liters per hour, 3.6 hours. Okay, so here's the spreadsheet. And as you can see, without the efficiency, the liters per day water use is 2.34. And then here's the flow per area or plant, 0.067. I think that's like 2 liters per hour. This is liters per minute, remember? And then here's the root zone depth, wetted diameter. And in this case, because it's a hedge, now we do have a distance between emitters, and then that's going to lead to a square-based calculation for the wetted area. So here's our available water, 14.4. And so the days between irrigations is 6.15. And that's different than the previous one because we just used this 2.34 instead of 2.9. But I'm just going to select 5 as the days between irrigations. So keep it the same as the problem. And then the irrigation runtime for a 5 days interval is 220, just like in the problem, or 3.66 hours. So I could also change my selected runtime to 264, and I can't remember why I did that. Oh, actually, I think I changed this before I changed this. I should have changed this back to 220 because now it's saying with 264 minutes, I have 6 days between irrigations. Okay, let's look at example 16.5. So in this case, we have 3 orange trees with 3 meters diameter and 1 orange tree with 4 meters diameter. Root depth is 1.6 meters, MAD is 0.5, landscape coefficient is 1.0. And in this case, we're going to use adjustable bubblers that can be adjusted for the diameter of each tree. So we can adjust the flow rate corresponding with the canopy diameter of each tree. And although the text goes through the screw adjustments for the emitters to get the precise flow rate, in this online example, we are just going to use the flow rates and not show how the emitters are adjusted. So the maximum flow rate or the maximum ET is for the larger plant, which is 4 meters. And so again, I divided by the efficiency, it's 160 liters per day. And then that's the 4 meter plant. And then for the 3 meter plants, 3 meter canopy, it's 90 liters per day. So then what you have to do is you'll adjust the emitters so that because it's a screw adjustment, you can get anything you want. You'll just have bubbler 1 flowing at a rate 160 over 90 times emitters 2 through 4. Okay. But even though we can adjust the emitters, the wetted area is the same. All bubblers have 2 meter basins. So the storage would be based on the 2 meter basins, or 281 liters. So here's the adjustment, or here's the spreadsheet. So in this spreadsheet, the water use was not divided by the irrigation efficiency. So the water use rates are 126 and 71 instead of 160 and 90. And the maximum flow rate for these types of emitters is 8.6 liters per minute. And so what you're going to do is just multiply 8.6 times 126 over, or 71 over 126 to lower the flow for the 3-meter emitters or diameter trees. And so those are 4.9. And the available water for all bubblers, because they all use the same 2-meter wetted diameter, is 283. So now the days between irrigations is 2.25 potentially for the large tree and 4 for the smaller trees. Well, what you're going to do is you're just going to design the system for the large tree, which is the worst case, which is always what you do in irrigation. You always design for the worst case, whether it's the summer ET or the largest tree or the farthest emitter, you always design for the worst case. And then, so now we have to select an interval of 2 days, because although these could go longer, if they're all in the same zone, they all have to be irrigated at the same time. So 2 days. They're all going to run the same amount of time because these have lower flow rate. So we have a nice uniform application, even though we had to select the irrigation runtime for the lower flow. So they all have the same runtime. Okay, so in this case, I have an orchard with many different sized trees, but no adjustable bubblers. Instead, we have to vary the number of bubblers under the trees. So we have 8-meter diameter trees, 4-meter diameter trees, 5-meter diameter trees, and 3-meter diameter trees. So what we can do is we can just put different numbers of bubblers under the different trees. And we're just going to say the maximum number of bubblers per plant is 7. And actually, it says the leaching fraction is 0.15 and the efficiency is 80%. We're not going to worry about that here. Okay, so in this case, the liters per day varies from 500 down to 71. So you can, and this is without the efficiency in the calculation. So this is with the 8-meter tree and 3-meter tree. And then we have to figure out a number of emitters per plant that's going to give approximately the same amount of water requirement to the different size trees. And so what I did previously is I figured out that if this is 7 and this is 2, the 4-meter plant, and the 5-meter plant has 3 bubblers and the 3-meter plant has 1 bubbler, then you get a pretty much representative flow rate considering the water use requirements. So then we can go through the calculation here. The wetted areas are quite a bit different because you have more bubblers. So here's the available water. And then, but the days between irrigations is about the same because we have much more wetted area for the larger tree. So as we can look here, it's slightly different, but I think if we choose 4 as our selected interval, then we're okay. And then our irrigation runtime is not exactly the same, but close. And if we just choose 45, we'll give all the trees the right amount of water. Okay, we'll see you next time.